So we took Sky on a walk at this really nice walk by Rockland High School. It's on the what they call Thunder Hill by Rockland High School. That I think that's Stanford Ranch. Or is that Park? No, that's Stanford Ranch. As you're going past, if you're coming from Whitney High School and you're passing Rockland High on Stanford Ranch, there's this little like, oh, it's by okay, now it is Stanford Ranch and Crest. There's a little green belt. Nice area to walk there. We call it the meadow. So Sky's looking off, gazing out at the end of the semester. And here she is in the green. The grass is so pretty right now. Out there, hopefully not getting any ticks. I don't know if it's tick season, but she's got tick medicine anyways. She's all right. And today we will work on chapter 7, continue to do that. I don't know if we'll finish 7, but we'll get close, I think. Oh, I'm on now, trying to open the iPad. And again, I keep saying this, it's best to, watch the lectures before lab if you can, but if you can't, at least look over the outlines like this one. Exam average. So I finished grading the exam. Average was 75%. I wanted higher. I want 80% average at least. So, but we are doing well. That was a harder exam than maybe the first couple. So we did all right. I want to still do better. So the high was 99%. And there were 4 scores over 90 and 16 that were 80 and 90 above, above 80. So that's about half of you got 80, about an 80% or above. That's good, but I still want more. I want everybody. I want at least an 80 average. Let's get there. And exam 3 corrections, they're due this Tuesday, Wednesday. Normally we do the corrections on the Wednesday, Thursday, but once again, our Tuesday, Thursday lab sections are missing another day. They're always missing days, the Tuesday or Thursday lab section. Thanksgiving, but it'll be nice to have some Thanksgiving time off. So remember to write out all the correct answers and write out correct answers for the questions and make comments on everything. Even if you didn't lose points, if I said, oh, you made a mistake here, or like correct this bond angle, but I didn't take points, write that out. And I want it to be, I think it's going to be better for you if you do it on a separate paper. So any problems you miss, write out the correct answer on a separate piece of paper. Some of you already do that. And others, they kind of like, since I made the quick correction to show where the error was, they don't write anything down, and I don't think you're getting as much out of it. So make your corrections on a piece of regular old piece of paper or on your iPad, whatever. Write out the correct answer. And then after exam 3, quiz plus. Like, now it's funny how things have become popular. Like I remember back in the day, hybrid was the thing. There was hybrid cars, and then everything was hybrid. It's a hybrid tablet computer. It's a hybrid pair of pants that turn into shorts. Everything was hybrid. Now everything's plus. The Disney Plus, you have Apple Plus. So today, or this week, we have quiz plus. After exam 3, quiz plus, because I want you to know how to do one particular problem in particular. And remember, when you're studying for this quiz, study questions you got right as well. So I'm going to give everybody on this after exam 3 quiz plus the question 4 from the exam. That's the one where it says, draw all of your regioisomers and then stereoisomers for this radical halogenation, that one, and then show how they all, in this particular case, you started achiral reactant, achiral products mixture. You show so I had maybe like 3 students who got it exactly the way I wanted on that one. A lot of people did pretty well. They got out of the 20 points, got like, 17 and above out of 20. But I want everybody to be 20 out of 20 on that. I think that the concepts in that question will help for the whole year. They really help. So you're definitely gonna have that one, the exact same question that you got on the exam. And that question was the same between both exams, whether you got the one exam or not. So study that, plus you'll get another question, one of the other ones from the exam. So it's going to be a double quiz, really, or after exam quiz plus. And it'll be worth double points, 10 points. So it should be easy points for you since you know the questions that are going to be on there and one of the 2 for sure. So just practice it. And I got a question. How to turn on Tuesday? Oh, good question. How do you turn in the corrections on Tuesday? Shoot. Good question. Ryan asked, how do we do the corrections by Tuesday if your first meeting and the only meeting of the week is on Tuesday? I didn't think about that. Darn it. Tell you what I'll do. Maybe I have to move it. I want to do it this week. Let me think about that, Ryan. Remind me. Thanks. Good question. Yeah, that doesn't make sense to have corrections on Tuesday before you have the exam. These darn Thursday missing days. I don't know what the school was thinking in the beginning of the year when we planned out to miss so many Thursdays. That's not but then everything else, power outages happened as well. And I decided to leave to take Michaela to college on a Thursday, but oh, you can come do lab work early as usual. Come in Monday, Wednesday, Tuesday, Thursday early. Let's try to finish and turn in the extraction lab this week. We've been working on that one forever now, and I have a couple turned in, but not enough. I feel like last week, this always happens during exams, students get caught up in studying and they're not doing as much lab work. And I actually have you doing other things as well, but I want us to really get the lab work done this week. And I know the Tuesday, Thursday, you're missing a lot, so we'll try to get through as much as we can. And I will give you all an extraction quiz next week because I want you to really understand how to do extraction diagrams. Some of you are getting there, many of you probably not, but we will now. So I have the monster extraction diagram. That was the one you had to fill out as part of the assignment. And I'm going to give you not the whole thing because it's pretty long. I'll give you a portion of it and you won't know which portion, but if you study the whole thing, you should be fine. And I'd like the chromatography experiment to be done by the end of the week. Wait, by the end of next week. Yeah. So I want to finish extractions this week. Let's get chromatography done next week. And homework, chapter 7 homework F. I'm almost done. That's why I came in late. I'm working on it right now. I'm doing a lot of good updates on these homeworks, adding a lot of good stuff, but it always takes longer than I want it to. So, but I'll post that today. So start working on that. When you start working on this homework 7, it starts off with basics, and then like these right here, you don't even need to have attended a single lecture. You're just copying down my examples, right? So start doing those early. It'll really help you understand the lectures. And yep. Okay, and then student of the week. We got a new student of the week. I've been like slacking on that. I keep thinking, oh yeah, I'm gonna grab someone to be student of the week, and then it's already Thursday at night, and I realized, oh, I didn't get anybody. But now I did. I got a good one. A Titan from Antelope High School, a bio major, will transfer to Sac State. We'll get a cool science lab job in the future. Does a lot of SPCA volunteer work, does not do, does. So volunteers for the animals, helping them out. Has a mini Aussie, a deaf wiener dog. Sounds like a band, Deaf Wiener Dogs. 2 cattle dogs and a Morkie. A Morkie is a combo. It's a Maltese maybe and a Yorkie. Is that what I'm thinking? Flexible shoulder joints because she broke her collarbones. Gymnast when young, reads a lot, an artist that draws and paints. Oh, and this reads a lot. Oh, this reads a lot. It seems like whenever I have students that are readers, the ones I see in the hallway reading between classes and stuff, they're always excellent students. So if you're not a reader, you should try it. You'd be surprised. It just makes your brain smarter. And then an artist that draws and paints. Here's a Zoe, one of the dogs. How cute. Huh? These pictures are so good. They look like they're from a magazine. And there's Bailey. And here's Frankie and Louie. And then Trigger. Trigger looks like he's ready to go. Like he or she, I'm assuming it's he, ready to fly. And our student of the week is Mia. Oh, she told me how to pronounce her name. It's not Mackie. It's like make. Oh, crud. It's Mia, our student of the week, and that's her and her boyfriend. So welcome to student of the week, Mia. Good job. I forget who was the last student of the week because it's been so long. Who was it? Was it? I don't remember. Oh, bad. If you're a student of the week, tell me on the chat. And then I got another question about how many labs do we have left? So we might have one more. I was hoping to do one more, the GCMS lab, which isn't too much on your end. So we got extractions and chromatography going now, and then I might add in the GCMS. Okay. Any questions about the intro? How should I do after exam quiz? I'll leave it up to you. That's what I'll do. Okay, here we go. For the after exam quiz for Thursday. Exam 3 corrections Tuesday or next. This Tuesday or next. You know what? I'll just make it next Tuesday. This way. This way the you have more lab time in that Tuesday lab. Next Tuesday and this Wednesday in lab. I think it's important for you to look over and correct your exam like right away, because you know we're building on that stuff currently. That's okay. Make my peace with it. All right, and then the after exam will be next Tuesday and this Wednesday. All right, there we go. Thanks for pointing that out to me, Ryan. All right, now back to our outcomes. Here they are. We're in chapter 7. Actually, I remembered I was in the middle of an example. I was going to do an electrophilic aromatic substitution, I believe. So let's see. It'll be on my Jamboard here. Is this one, huh? Yep. Go to today's Jamboard then. All right, let's look at this to review. So we're talking in this case about an E1 reaction. E for elimination, you're eliminating a hydrogen. That's, well, actually just the proton of a hydrogen. That's one carbon away from the carbon with leaving group. Carbon with leaving group, one carbon away, one carbon away. You're eliminating the hydrogen and the proton of the hydrogen and the leaving group. So let's look at this first regioisomer here, this mono substituted alkene. And how many hydrogens are on the methyl on the left here? There's 3 hydrogens right here for the methyl in the reactant. How many now does it have on the product? 2. Good. So it lost the proton of a hydrogen here. And then on the leaving group carbon, it had a leaving group. And how many hydrogens does this leaving group carbon have? It has 1 hydrogen. How many does it have on the product side? 1 hydrogen here. Still got 1. So it does not lose the hydrogen that the leaving group carbon has. It doesn't lose it. It's always 1 carbon away. Now let's look at the other 2 products. The cis alkene, when the methyls are on the same side, they're called cis, and the trans alkene when they're on opposite sides. So the cis alkene, okay. So let's talk about first this carbon here. How many hydrogens does it have? 2 hydrogens there. And now when it's here, maybe it's easy to see here. How many hydrogens here? 1. So again, it was losing a hydrogen, the proton of a hydrogen, 1 carbon away. What about the leaving group carbon? How many hydrogens does it have? 1 hydrogen. How many does it have now? Still 1, doesn't lose it from there. All right, so we went over our mechanism. First step was the leaving group leaves, boom, and we get a carbocation. How many hydrogens does this carbocation have? 1 hydrogen. And what kind of geometry is this carbocation have? Trigonal planar. And what kind of carbocation is this? Is this a methyl carbocation, a primary carbocation, or secondary carbocation, or tertiary? Tertiary carbocation, yeah. I mean, secondary carbocation. I don't know why I said tertiary. Secondary carbocation, yep. And our ethanol coming by, it's a weak base. It had to wait around for the carbocation to form. Like the ethanol wasn't strong enough to deprotonate while the leaving group was on. Once the leaving group pops off, that slow rate determining step, once that leaving group pops off, then this carbon is drawing electron density really strongly towards it, pulling electron density towards it. These sp3 carbons are helping out. Oh, I can help out. I'm electron donating. They're donating electrons in. And so the carbon to hydrogen bond is lacking electrons. Electrons are being pulled towards that carbocation. These electrons, you could think of them as like the glue. They're the glue that hold atoms together, right? And if the carbocation is drawing away that glue, that makes this bond much weaker, more acidic. So even the weak base can deprotonate it now. Boom, boom, get our mono substituted alkene. And then for this other one, same thing on the other side. This is an sp3 carbon donating electron density, stealing some of the glue from its carbon hydrogen bond, making that bond weaker so the weak base can come and deprotonate it. Boom, we get our cis and trans because this carbocation is not stuck in this zigzag form. It can also be this way. And before the leaving group leaves, it can be rotating around, right? So you get both the cis and the trans. So with that idea, let's draw the reaction coordinate diagram. Let's see here. Trying to change the size of this guy, but it won't let me. I guess I gotta pull it up. Okay. I feel the shift in our class. I feel like we're becoming more and more like true organic chemists now. I could see it when I talk to you in lab and stuff. You're starting to get it. It's nice. I hope you're starting to feel it too. I like when it gets to the point where we're not just like memorizing things, we're understanding. Okay, so the first step, let's start like right here, say. I've got my electrophile, and it's just reacting by itself. And the leaving group's just going to pop off. Is this going to be exothermic or endothermic? I'm seeing 2 endothermic answers, and that is correct. And I got a question over here. Yeah. All right, so the first step is definitely endothermic. Why is that endothermic? How do you know it's endothermic? We know it's endothermic because it only involves breaking a bond, and it takes energy to break bonds. Okay, next up, we add the ethanol, and that will deprotonate 1 carbon away. And there's a few things I'm going to show you here that you wouldn't be able to predict yet, but I'll help you with it. This next step is going to be exothermic. Now, you wouldn't really know that because there's a bond breaking and a bond forming. You'd have to look up bond energies, but that's what it is. And the products, the 3 products are at different energy levels. They're not all the same energy. Let me show you. The highest energy product is the mono-substituted alkene. Then the next highest is the di-substituted cis, sorry. Cis, and then finally the lowest energy is the trans. This I don't think I've told you this yet, but this is the case. Substituted. Now we say mono-substituted. What that means is that the alkene has one alkane chain in place of a hydrogen. So that's a mono-substituted alkene right here. And then this one is called a di-substituted because it has two alkanes in place of a hydrogen attached to the alkene carbons, the two alkene carbons. It's di-substituted. And also it's cis. The two groups are cis to each other. The two methyls are on the same side. That's going to be higher in energy than when you have di-substituted and the two groups are on the opposite side. So to predict that the mono-substituted alkene having replaced, one of the four hydrogens. So imagine, let me draw over here. So I'm just like, this is an unsubstituted alkene, just ethene here. If I have an ethene molecule, ethene Ni, I tell you that this is unsubstituted, not substituted. What I'm saying is it has 1, 2, 3, 4 hydrogens attached to it, nothing else, unsubstituted. Then when I substitute one of the hydrogens for an alkane, it's mono-substituted. When I substitute two of the hydrogens for an alkane or other groups too, it's di-substituted. And then here it's di-substituted again. For you to predict that, oh, monosub's higher in energy than di-sub, I wouldn't think you'd know that yet. But I think you can explain why the di-substituted cis is higher in energy than the di-substituted trans. Why do you think that is? These two methyls are close to each other. They're like bumping into each other. They have more steric hindrance. Than trans. Okay. And then let me make sure I don't forget all my products here. I also have to draw in the protonated ethanol for these too, huh? Okay, so now the activation energy for all these, it's about the same. And it doesn't, we're going to find out it doesn't really matter so much for this reaction what the activation energy is to us, because the major product isn't dependent on that activation energy. So I've got some activation energy here. I'll call this transition state 2. I'll call this one 3, and I'll call this one 4. So the activation energies are all about the same. And it turns out the lowest energy product is the major one. So you'll make more of that. Okay, before I discuss that, let's draw some transition states real quick. So the first transition state looks mostly like products. So the iodide is going to be far away, huh? And the iodide's building up a negative charge. It's going to be almost fully -1. I'm going to say it's like -3/4. Where the carbon's going to almost be +1. It's going to be like +3/4. Okay, and now this next one is a tricky one, the transition states 2, 3, and 4, because they have a lot going on here. So for the first one, it's looking like reactants. So the ethanol is going to be far away. I'm going to draw this up higher. Ethanol is going to be pretty far away from that hydrogen it's grabbing. And then the hydrogen is breaking a bond to carbon, but but it's the hydrogen's still pretty close to the carbon, and the pi bond is starting to form. You got to remember that pi bond that's starting to form. It's easy to forget that one. But remember, we show dots for every bond that's forming and every bond that's breaking. Okay, and now for charges, the oxygen of ethanol, it starts off 0, and it's still close to 0 because it's looking like reactants, this transition state, right? So it's building up some positive charge, but it's only like plus a quarter. The carbon, though, is starting off +1. It's only just starting to lose that positive, so it's plus 3/4. Okay, and now the other ones are looking similar. So transition state 2 is done. Transition state 3 is again looking more like reactants. So I got the oxygen here, and it's going to be taking this hydrogen here from there. There it is. So that's going to give me my that's actually transition state 4, huh? Let me fix this. That was leading to the trans product, huh? Let's go like this. And you know what? I'm going to draw this differently. There we go. That's looking like the trans product, huh? Or the cis product, huh? And our charges will be the same. It's looking more like reactant, so it's like plus a quarter for the oxygen and about plus 3/4 for the carbon. Let's see if I can draw these nicer, make sure it's readable. Plus 1/4 for the oxygen, plus 3/4 for the carbon. Got it. All right, the last one, it's looking just the same, huh? But it's going to have the trans. That hydrogen's far away. Okay, got it. So now what's the deal with these energies? The deal is the following. I got a nice animation I made up this weekend. I was trying to make up an E2 animation, Google slide animation. And then I thought, oh, wait, I got to first explain this, the energy of these alkenes. And then that took up the whole weekend. They're like Pandora's boxes, but when they're done, they're good, I think. I hope they're helping you learn. Substituted alkenes, that's what I want to talk about. Let me do this. I wonder if I copy this so you know later if you're going through the Jamboard. All right, yeah, that's what we're going to talk about now. So come over here. So I'm going to have you click through this as part of your homework, and it's one of the questions I've added to the updated homework. And thanks, Ryan. And then, so this is I'm not going to go through the whole thing, but I'm going to get you to the main points of it, and you're going to click through and do this for the homework. It'll really help you out. So this is an unsubstituted alkene because it has hydrogens on all 4 positions of the alkene, of just one alkene like this, right? Unsubstituted, only hydrogens. And then a monosubstituted has, one thing replacing a hydrogen, in this case, a methyl. And then I go on to disubstituted, trans, and cis, right? These are diastereomers. Boom, boom, boom. And then this is the new thing here. Let me actually get this all on here. Ugh. Okay, I like my animations, but I think to see me draw stuff out on the Jamboard and the live lecture is also an important, different way to learn it. If I just gave you the Jamboard, it's only one thing. All right, so here we go. So I got these guys. These are all dye substituted. And someone tell me why this out of the dye substituted, this is the trans is the lowest energy dye substituted. Why is that? Compare, I'm saying this dye sub is lower in energy than the cis dye sub and then the geminal dye sub. So the geminal dye sub, that means the two substitutions are on the exact same carbon. So they're like twins, like the sign Gemini, they're twins. Positive, mutable sign, flexible, responsive, superficial, and witty. Oh, superficial. I don't know if any of you are Gemini. I don't even know when Gemini is. I think it's funny whenever you read about the signs, there's always like something that it can probably apply to everybody. But I don't know, maybe there's some too, who knows? So here, the two groups are further apart when they're trans. So there's less steric hindrance because this ethyl and this methyl are both atoms with negative electron clouds on their outside. When the ethyl and methyl are on the same side, their negative electron clouds repulse each other more. So more steric hindrance. So this would be the lowest energy of the dye sub because it has the least steric hindrance. And then the geminal is the highest energy. Geminal meaning, again, Gemini on the same exact carbon. Highest energy on this slide, they have the most steric hindrance. When you're on the same carbon, you're even closer than when you're on cis across the double bond. So these two, this methyl and this ethyl are pretty close. They're like really pushing on each other. Okay, so let's see. I think I try to show that with arrows and stuff. Yeah. Then there's tri-substituted. We have three things, and then there's di-substituted. I mean, tetra-substituted. We're all four. All right, let me get to the end here. I'll do the energy thing first. Yeah, I'll do this a little different. This one's pretty good. So it turns out the more substituted you are, the lower in energy you are. We saw that on the E1 example I just did. And the so what kind of alkene do I have here at the bottom that just dropped in? Is that a unsubstituted, monosubstituted, disubstituted, tri, tetra? This one is tetra because it has 1 methyl, 2 methyl, 3 methyl, and a terbutyl. Has 4 different things. Tetra substituted. It's very low in energy. Now, why do I consider it? Why do we find it's lower in energy experimentally, but then how do we rationalize it afterwards? What do we think? So the way I think of it is, I think I got it. Well, actually, let me just finish this. I'm all over the place here. Let me just do this. So what's this next one? That's a little bit higher in energy. This next one is tri-substituted. It's got an isopropyl, a methyl and a methyl, and 1 hydrogen still on the alkene. So that's a tri-substituted. And then this next one, what is it? Describe it with 2 terms, not just the substitution, but the other term too. It's di-substituted and trans. Oh, and it's also called the E-alkene. I'll explain that shortly. And this one here, what do we have? 2 terms for this one. What do we call it? it's not mono-substituted. It's still di-substituted because it has a methyl and an ethyl, 2 hydrogens. So di-substituted and cis, or Z. We'll see what Z means shortly. Then this one, what is this one? So this one, they're both, it's di-substituted again, but they're both on the same carbon. It's like they're twins. And I guess maybe because they're like a methyl and ethyl, they're not identical twins. They're paternal twins. Is that what you call them when they're not identical? I don't know. But these are geminal di-substituted. So fraternal are non-identical twins with F? Okay. I don't know. Yeah, and so geminal disub are the highest energy of the disubs because they have the most steric hindrance when they're on the same carbon versus across. Then next up, what's this one? Oh, I didn't mean it to come up. Mono-substituted. Finally, unsubstituted is highest energy. Okay. Let's go back to my Jamboard here. Looking good. And you'll see I listed the di-substituted trans as the lowest energy of these alkenes. And then the di-substituted cis higher in energy because of steric hindrance. And finally, the monosub as the highest. Okay, so another thing we need to talk about with these alkenes. We got some more nomenclature to do. So tell me what kind of alkene this is. What sort of alkene is that? This is a tri-substituted alkene. You're right. Okay, it's tri-substituted. I got it. Should we call it cis or trans? So I can see there's the two isopropyls are cis to each other. All right. But the propyl, the N-propyl, I'll make sure you understand what those are shortly. Is trans to the an isopropyl. Wait a minute. So let me circle these, show you what I'm talking about. So on the left here, I've got this right here is an N-propyl. This over here is an isopropyl. When it's a snake tongue kind of thing, it's called iso. And then this over on the other side is also isopropyl. So it can be confusing to call this molecule cis or trans. So we don't do it. Oh my God. Bambi. Confusing. We don't do it. And we only use cis or trans for di-substituted alkenes and rings. You know, like when things are attached to cyclohexane, they could be cis or trans to each other. So for tri-substituted, we don't say cis or trans. We need another type of nomenclature. For tri and tetra-substituted alkenes, we use the E and Z nomenclature. A new nomenclature, a new stereochem. Now we have R and S for tetrahedral stereocenters. For alkenes, we use E and Z. And it's actually much easier than the R and S. So I'll show you what I mean by that. Let's go. I think I've got a nice summary of it. Yeah, here it is. I'm looking for the German words here. There it is. So we use E and Z because we use Z for the German word zusammen. I don't know if I'm pronouncing it right. It's together. I guess that word in German means together. Does anyone speak German? Does that sound correct? And the German word Antigenen, I don't know how to say that either, but the E from that, I guess that means opposite in German. Okay, so Z and E, what's the deal? What you have to do to get the E and Z determination is you have to look at each side of the alkene separately and assign priorities to the group. So on this left side, the blue side, if I were to assign priorities, do we have any rules to like assign priorities to groups that we can use that we've already learned? To say, oh, should I consider the N-propyl higher priority or the isopropyl higher priority? Is there any rules we can use that you know? Yes, we're going to use the same Ingold-Prelog rules that we use for stereocenters. The ones where you go stepwise and you first look at the number, the atomic number, you know. So yeah, we already have rules for this. So that makes it easy. So when I start off and I compare one side at a time. So imagine I'm going to cover up one side of this. Let's see if I can do this on this thing. So I'm going to cover up this side first because sometimes students get confused. They want to assign all the sides at once. Oh, it's not letting me cover it up. It's so weird. I think I have to grab something with color. Let me snatch some of this border on my. Come on, there we go. Can I cover up things? Yeah, I can cover up things. That's pretty good. I like that I can kind of cover it up. I like it. There we go. So I'm going to cover up the right-hand side first, and I'm only going to consider the left side. So what's the higher priority? I've got a carbon initially and a carbon initially tied. What's attached to this carbon? A hydrogen, and a carbon. To this carbon, 2 carbons and a hydrogen. So who's higher priority? The top group, the N-propyl or the isopropyl? What's higher priority? Yep, it's that. It's the bottom one here. Let me change the color so it jumps out green. Okay, so higher priority over here. Okay, that's my higher priority. Boom, I'm going to box it. Got it. All right, so now I've got that side done. Now I'm going to try to cover up this side and ignore it because I don't want to. I want to just do each side independently. So I'm covering up all this, and then I look over here, and I've got a hydrogen versus an isopropyl. What's the higher priority on the right-hand side? it's going to be the isopropyl, right? Because that carbon beats out the hydrogen. Got it. Okay. So I've determined my two sides, right? And now I can name this guy. I can add stereochemistry to it. What kind of alkene is this? This is a alkene that has its higher priorities on the same side. Instead of saying the, I'll say it with a thick German accent. The highest priorities are on the same side. They are together. Zusammen. So this is the Z alkene. So that's where the E and Z, not too hard, huh? So it's the Z alkene. And then once I know that, I can draw the molecule again if I like. Let me draw it in blue this time. I got my alkene again. I've got my lower, oop, I'll make it look the same. Boop, 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 boop. I got that left side done. And now what if I put the isopropyl here instead of going down like it was? I've switched the isopropyl on the right with its hydrogen on the right. Now, when I look at these two, I've got my highest priority on the left, trans to the highest priority on the right. So should I call this trans molecule? No, because trans would mean I'd have to say, oh, it is. I mean, if you really wanted to say, if you're just talking to someone, you can say, oh yeah, my isopropyl is trans to the N-propyl. That would tell you, but we don't want to have to go through all that full sentence. We're just going to instead call this alkene here the this particular alkene is the E alkene, because the two groups are opposite of each other. They're not on the same side. It's the E alkene, and E meaning opposite in that German word. Okay, how are the two related? Are these two molecules the same molecular formula? Do they have the same molecular formula? Same molecular formula, they're isomers. Do they have the same connectivity? Yeah, looks like if you were to count along, 1, 2, 3, 4. Yeah, they got the alkenes between 3 and 4. And do they have different three-dimensional arrangement? Yes. Are they mirror images? No. So they are diastereomers. Okay, so I'm not giving you the full name of this alkene because we're not going to go over alkene nomenclatures till later, but I can just show you real quick. We'll confirm it. Let's see if SDBS agrees with this. I'll do this one since I've kind of got it partially drawn up here. Oh man. Let's go boop, boop. This isn't SDBS. This is a Marvin sketch. Let's see if Marvin agrees with this. All right, am I drawing that one that you see on the right? I'm drawing the one down here. Yeah, I got that one right. Okay, let's do this. Structure to name. There, yeah, there we go. Okay, let's see what we got. So I said this one was an E alkene. Let's see what Marvin says. Yep. Marvin's going with 3E, 4 isopropyl, 2 methyl, hept, 3-ene. Yeah. So we'll learn. I'll go over more slowly the nomenclature rules for this stuff in chapter 11 next semester. But I thought I'll show you now. Why not? So 3E. So 1 isopropyl. So it's 3, 4. Yeah, it's counting from, say, like here. 1, 2, 3, 4, 5, 6, 7. Heptene, right? Longest chain. So we got the 4 isopropyl. That looks good. 2 methyl. Hept 3ene. So the alkene starts on carbon 3. There it is. And it's E. The main thing I wanted to know is E. All right. So last thing I want to talk to about this substitution stuff is just why I think my rationale as to why there are the more substituted alkenes are lower in energy. This is what I think. This is what I think. I think it's because a sigma bond, which has electron overlap in the internuclear axis, meaning here's a carbon atom, its nucleus is right there with its protons and neutrons, and here's the other carbon atom, its nucleus is right there, protons with its protons and neutrons. The electrons overlap right between the two nuclei in the internuclear axis. You got really good, strong electron-electron overlap, holding it together. And you can actually rotate this sigma bond. It doesn't break it. We do Newman's looking down these and all that. Whereas a pi bond, it's the second bond of the double bond. We got our sigma bond here, but our pi bond is overlap above and below the internuclear axis. So instead of letting all your electrons be like concentrated along the internuclear axis, you got to put half up top and half down below. But it's still just 2 electrons in the sigma bond, 2 electrons in this pi bond, right? It looks like maybe it'd be 4 electrons, but nope, 2 electrons total. So you have your electrons spread out over a greater area. And so my thought is these pi bonds are all kind of short electrons. They're like, oh, we have to put some up top, some below. Wish we had a little more electron density to help us, right? And we've talked a lot about things that needed electron density to help them. What kind of things did we learn about so far that are short electron density that want more electron density? First, the radicals. Remember, radical carbons that are short electrons, they want extra electron density. And then carbocations too, they're short electron density, right? What kind of groups did we say help these electron deficient atoms or groups or things? sp3 carbons are electron donating, right? There we go. So if a pi bond has 4 hydrogens around it, unsubstituted, these hydrogens are like, yeah, you're short electrons, whatever, I'm not helping you. But then when you look at a substituted alkene, like say this tetrasubstituted alkene down here, it's got 1, 2, 3, 4 sp3 carbons donating electron densities to that pi bond to help give it more electron density. I think that's why it's lower in energy. Whereas then when you go to a tri-substituted, it's got 1 hydrogen there. It's only got 3 sp3 carbons donating to it. Di, it's only got 2. Mono substituted, only 1 sp3 carbon donating into that pi bond that's kind of short electrons. Do you like that concept? Does that make sense? I try to like tie these ideas from like radicals to carbocations to pi bonds all together, you know? Good. All right. Okay, cool. Here, let's do this one really quick. This is a good summary one. So I've got what kind of alkene here? How many sp3 carbons are donating to that pi bond to make it more stable? What sort of alkene do I have here? Is this a mono substituted di? Let me see, I got a methyl, isopropyl, methyl, isopropyl. Oh, that's 4 things attached to the alkene, huh? So this is a tetra substituted. Tetra. This alkene has no hydrogens attached to it. It's tetra substituted. 1, 2, 3, 4. Remember, tetra is 4, like a tetrahedron has 4 groups, or the game Tetris has 4 shapes. Tetra. All right, so we got 4 groups. And then are these 4 groups going to be E or Z? So let's see. If I cover up the right side, ignore this right side, what's a higher priority? Isopropyl or methyl? Isopropyl is higher priority. On the other side, what's higher priority, methyl or isopropyl? isopropyl. So the isopropyls are not on Z same side. They're on opposite sides. So this is the two highest priorities on opposite sides. This is the tetrasubstituted E alkene. Okay, what about this next one? What kind of alkene is that? Is that mono, di, tri, tetra? It's a tetrasubstituted alkene, yep. 4 different groups attached to that alkene. And the 2 higher priority groups are on Z same side. So this is the tetrasubstituted Z alkene. So they're both tetrasubstituted. That makes them low in energy, but the Z is higher in energy. Why is it? Because they're both these 2 higher priority groups are also the largest. This isopropyl is much larger than a methyl. And to have the 2 large groups on the same side, there's a lot of steric hindrance there. What about this one? What kind of substitution does this one have? How many carbons are attached to that alkene? I see you're saying 1, Ryan. I hope you're saying 1 hydrogen's attached to the alkene. Because I see a methyl, a CH2, a methylene, and another methylene. So I see 3 carbons attached to the alkene. That's a tri-substituted alkene. And we could go E and Z on this, but you don't normally in a ring because it can't really be the other one. But if I was going to call this E or Z, let's see, I got a methyl and I got a CH2C. Oh yeah, that's higher priority. I got a hydrogen. This would be E or Z. This is a higher priority. That's a higher priority. What would you call this one? Higher priorities are on Z same side. But for this 5-membered ring, you can't really, it's too small of a ring. You can't have this part of the ring being over here. It would have to really stretch around. So you don't really call it Z. But if you call it Z, it's not wrong. What about this one? How many carbons are attached to it? It's di-substituted, good. And are they on the same side? They're on Z same side, that's right. So we can call this a Z alkene, but we can also call it something else. We can call it the cis disubstituted, and it's also the Z alkene. So the E and Z can apply to everything, but cis and trans only applies to disub and rings. Okay, this one's another disub, but it's a little higher in energy because it still has 2 electron donating groups, but it's got more steric hindrance than the cis. And this one's the geminal disubstituted. You wouldn't use cis or trans for this, just geminal. And you wouldn't use E or Z because you need something different on either side. And then finally, the highest energy, the one with only 1 group electron donating sp3 carbon to the pi bond. That's the monosubstitute. Nice. The end. Okay. And I don't think I pointed it out, but remember, sigma bonds can rotate. They do have to overcome eclipsing interactions, but there's enough energy normally around it to rotate around, right? Where pi bonds, they can't rotate. I mean, they can, but if they do, it's a reaction. You're creating a different molecule because of the pi bond has overlap above and below the internuclear axis. It would have to break the pi bond. So we left off with E1. We went on a little side adventure on the different substituted alkenes and their energies, but it was related to the E1 reaction. Let me summarize a few things before we're going to finish up E1 and then we're going to get into E2, but let me do a little summary here. I'm going to go to the chapter 7 slides. PowerPoint's taking its time. Okay, now we're good. So for E1, it's very similar to SN1. So remember, for SN1, it's all about the electrophile. because the electrophile has to lose its leaving group for things to get going. And in E1, you have the exact same first step, losing your leaving group. Let's actually look at this really quick. This will be a nice summary to get us going. So for SN2, we'll take a step back. SN2, it's a backside attack, and steric hindrance is the key. So if you have a methyl electrophile, it's great for SN2. You got a big cone of reactivity, nothing but room. You might miss the cone, but if you hit in the cone with enough force, enough energy to overcome the activation energy, you get your product. SN2 happens fast with methyl electrophiles. And then also primary electrophiles, still plenty of room. There we go. Get in that cone of reactivity. The cone of reactivity did get smaller, but it's still big enough and fits like a glove. And then for secondary, the cone of reactivity is getting smaller, but if you're a strong nucleophile, you can still do it. It might bounce off a few times, but if you get the right backside attack, you get your SN2 reaction to occur. Tertiary, now the cone of reactivity is so small, not enough room. This is like Galleria Black Friday shopping in a few days. You're just going to avoid that. So if the glove don't fit, you must have quit. Or if the nucleophiles, if the cone of reactivity is too small, can't do SN2. And now for SN1 and E1, it's all about the carbocation. And so again, it's about sp3 carbons and their electron donations. So do carbocations have an octet? Nope, just 6 electrons. Can sp3 carbon neighbors help? Can they donate electron density to stabilize a carbocation if they're attached to it? Yes. So the methyl carbocation is the highest energy carbocation. It's actually so high in energy, it's up by the moon. And then right below that, orbiting the moon, is the primary carbocation, still so high in energy that we don't want to consider it as a carbocation. We don't want to have a mechanism where we make a primary carbocation because they're just so high in energy. But secondary carbocations, now they're close enough and low enough in energy that we can consider them for our reactions. So they have 1, 2 sp3 carbons donating. And the tertiary is the lowest energy carbocation. That one has 3 sp3 neighbors donating to it, helping it out. Okay, and then we have the catosphere again. Tertiary carbocation. Reach for the stars is the tertiary grumpy carbocation. Just wear deodorant. And then the secondary can happen, but the primary is too high in energy. See this SN1 and E1, they can jump up and reach tertiary and secondary. They can't reach primary. You reach me, says the grumpy primary carbocation, when your mom flies. Or the methyl carbocation, think you'll reach me, says the methyl grumpy carbocation. That lipstick on your forehead won't help you make up your mind. So, all right, we got that. So here we go. Methyl carbocation. Can I be a carbocation? I wish I could be a carbocation. Let's see. If you're wondering, try drawing out the mechanism. Help. Nope. Busy. Nah. Too high in energy will not happen. So don't draw curved arrow mechanisms or reactions with methyl carbocations involved. So no SN1 or E1 for methyl electrophiles. What about primary? Can I be a carbocation? Let's see. We got a primary carbocation. Help. No. Sucks to be you. Oh, sweetie, I'll help you. So it's got 1 sp3 carbon to help. But is that enough? Nope. Too high in energy still. Can't happen. Okay, next, secondary carbocations. Now, can I be a carbocation? Boom. Help. I'm your wingman. Psst, whatever. Gotcha, homie. So 2 neighbors, sp3 carbons donating, can it form? Yes. Carbocation, you shall be my secondary child. So yes, it can be a carbocation. Tertiary now. Can I be a carbocation? Help. For sure, bruh. I got you. I got you. Started from the bottom now. The whole team's here. So tertiary on, play a God's plan. God's plan. So yes, you can be a tertiary carbocation. We got it. Okay, so here we go. The carbocation can form. What kind of carbocation is this one? or can this one form? What is this? This is a secondary carbocation. And once you form that secondary carbocation, it can do two things. It can become an electrophile for an SN1. Boom, there we go. And when the methanol electrophile, which is a weak electrophile, when it comes in, it can come in wedged or dashed, so I can draw wiggled, and then it can be deprotonated. Give me my ether. So now an oxygen's got a carbon on ether side. A racemic mixture of ethers. So we make an equal mixture of the wedged and dashed because that trigonal planar carbocation is the same on both sides. So also notice this methanol is a weak nucleophile. It doesn't have a negative charge. So it couldn't do SN2. It had to wait. It was just waiting around, kind of kicking the pebbles like, oh, I wish that electrophile would dance with me. And then it was too weak. But then when the leaving group left, it's like someone spiked the punch bowl. Now the methanol is like, yeah, I'm getting drawn in there. Boom, adds to the electrophile. All right. Okay. But also, yeah, cool. And this SN1 reaction, it's favored under cool conditions. I'll explain why shortly. Next up is the E1. So the E1 is where the same weak nucleophile is also, in this case, a weak base. And this weak base could, instead of hitting the carbocation, it might hit one carbon away or one carbon away. And if it hits that hydrogen there with enough force, it can cause the E1 reaction to take place. And if it attacks this side, we get the monosubstituted alkene, a little bit higher energy. If it collides at the other carbon, one carbon away, you can get the disubstituted alkenes, the trans and the cis. Okay, and so all three of these things can happen with methanol. If you heat up the reaction, it favors the E1 products more. So E1, it's getting hot in here. So I'll explain why that is shortly, but cooling a reaction that has a competition between SN1 and E1 results in more SN1. Heating it results in more E1. Okay, let's talk about it. So before we do E2 though, let me back it up. SN1. When the reaction is cooled, it helps to favor SN1. I'm gonna go this way. When the reaction is heated, it favors E1. All right, and I got a nice analogy for you. I like this analogy. So when I was a kid, I remember we lived in some apartment complex. We moved a lot. Every year we moved. But when we lived in this one, I don't remember which one it was, but it had a ceiling fan, and the ceiling fan was above me. And the ceiling fan's spinning around, right? I'm not sure. Let's just put fan, right? So the fan's spinning around. And here's Mark laying on the ground on the carpet. Because the TV's right here and we didn't have a remote, so you just like reach your foot up to change the channel. And then I'm like one of those kids who like always doing a bunch of things at once, you know. So I would take a say I had like a wiffle ball, and I'd throw it up in the air and try to make it go through the fan blades and back down without hitting the fan blades. And I thought it was interesting if you could throw it. And a lot of times it would miss the fan blades. It would miss it on the way up and miss on the way down. I thought that was cool. If it hit the fan blade, it would just get like, it would go and shoot across the room or something, right? It's kind of fun. Okay, so what if, say like my brother came in and he, before he tried to pin me down and like put his armpit in my face until I said uncle, which I never said uncle. So if my brother's coming in to mess with me, but he say he turns the fan faster, turns on the fan faster, what happens there? Let's see. Fan slow. Do you think when the fan is going slow, it's more likely that the ball can make it through, or is it more likely the ball will get hit? I think it's more likely the ball misses the fan. And I did have a cat, Kitty, our little gray tabby cat. She's the best. She's the sweetest little cat. We had her like 16 years. Okay, and then fans fast. I think the more likely the ball is hit. So my brother comes in and turns up the fan faster and it hits it, you know, whatever. So let's go blue on this one. So when the fan is slow, the ball can make it through and miss more often, right? And when it's fast, it can get, the ball hits it more often. Yeah, and I'm using this fan to represent heating and cooling of the E1 and E2, SN1, SN1 and E1. Also, but before I do that, I think this is pretty cool. The original fighter planes from like World War I, probably in World War II as well, they had propellers going round and round, you know, and they put their guns. This takes a lot of confidence. The guns would shoot through the propellers. And they would time the firing of the bullets with the spinning of the blades. It seems like just crazy because if something's off, if you're like bullet, when you squeeze the trigger, it fires a little too early or a little too late, you're going to shoot off your propeller and then down you go over enemy territory, right? But they figured it out. So yeah. Now, how does this relate to SN1E1? So let's look at this. I'm going to draw up a tertiary carbocation here. I'm going to draw it a certain way. I got my methyl here, my methyl here. Oh, I didn't draw that very good. Tertiary electrophile, sorry. The tertiary electrophiles, they're excellent for SN1 and E1 because they have 3 sp3 carbons ready to donate electron density after the leaving group leaves. So my leaving group leaves, I go from being tetrahedral to, or the electrophile goes from being tetrahedral to trigonal planar, right? Okay, so it was tetrahedral here. Use a different color for that. Tetrahedral, now it's trigonal planar. And let me draw out one of these a little better too. Okay, so now let's say my nucleophile happens to be like water, my nucleophile slash base. So this water here is a weak nucleophile and a weak base. It had to wait around for the carbocation to form. It was too weak to do the SN1 or SN2 or E2 before the leaving group left. So that weak nucleophile, weak base, it has two options. It can come in and do SN2, right? If it avoids these hydrogens that are one carbon away, it can do E2, boom, if it hits there, right? It can also do E2 if it like slips between the fan blades. Not E2, SN2. Why am I saying 2? Oh my goodness. Sorry. Not 2, 1 for these. It can do SN1 if it hits the carbocation there. It can do E1 if it gets and it hits the hydrogen right there, right? Or it can do SN1 if it gets past. So if the water comes like straight from above, oh, it's SN1 all day, right? No problem. If it's coming from the side at an angle, it has to miss these hydrogens. If it can slip past them, it can do SN1 still. But if it hits into one of the hydrogens, it does E1. So is this starting to make sense? Next slide. So think of the methyl and its 3 hydrogens as a fan. This is the methyl that's, you know, yeah, that's good enough of description. So if that's a fan, then when you heat the fan, when the reaction is heated and the methyl spins more, and the water will hit the hydrogen 1 carbon away more often. Reaction. What's the action? It's cooled. Oh my goodness. Methyl and spin slower. Water slip. Past the hydrogen often. Into more. SN1. Does that look good? I like that analogy. So if you want to run an SN1 reaction, you're almost always going to have competition with E1. If you want the SN1 product, you just cool it. If you want the E1 product, you heat it. Pretty nice, right? Okay. I'm wondering about the E2. Let's just look at the E2 on the slides and then I'll end there. So E2, we'll end with this one. So E2, you think sterically hindered strong base. And E2 electrophiles, let's go through them. So a methyl electrophile, can I do an E2 reaction on a methyl electrophile? So for E2, I need a strong base to come along and deprotonate 1 carbon away. So here's my carbon with my electrophile. Is there a carbon 1 carbon away? No. 1 carbon away, wait, only 1 carbon. You need at least 2 carbons to do E2. So I don't always E2, but when I do, it's with at least a 2 carbon electrophile. All right, and then primary electrophile. So primary electrophile, can I do it? I got a carbon with a leaving group, 1 carbon away. Oh, I got a hydrogen there, yeah. 1, nice. I got 2 hydrogens that are 1 carbon away. I've only drawn 1 here for the mechanism, but there's 2 hydrogens there, right? Boom, put a little hinge on there. E2, got it. What kind of alkene did I just make in this E2 reaction? Monosubstitute alkene, yep. And talking about this base here for the E2, is it sterically hindered having this torpedo group, the 3 methyls? Yes, sterically hindered. So that's good because that'll make it not be able to do SN2 as much. So it's going to do more E2. Also, is it a strong base? O minus. Seem like a strong base? Yeah, it's got no resonance to stabilize it. It's on a smaller atom oxygen, so it's not spread out over a big area like, say, a bromide or something. All right, so this is a strong base, sterically hindered. It's good for E2. And it's strong enough that it doesn't have to wait for a carbocation to form. Well, this would be a primary carbocation. It wouldn't happen anyways, but it doesn't have to wait for carbocation. It can just go deprotonate right away. Strong base. So I think it's like a hippo. Us chunky bases prefer E2. Too much traffic on the interstate SN2. So SN2, you have to go through the cone of reactivity, right? And I think, aren't hippos like one of the most dangerous animals in Africa, I think? I think they're really fast and aggressive. They look so cool and friendly, but I don't know. Okay, now E2 with secondary. Can it happen? I need a carbon with a leaving group. I need 1 carbon away. I need some hydrogens. Do I have them? Yeah, I do. I got actually 6 of them. So this guy right here, does it look like a strong base? And does it look sterically hindered? Looks really sterically hindered with the 2 isopropyls. Is it strong? Yeah, and N minus is much more strong than O minus. It's to the left of the periodic table. It's not as nitrogen's not as electronegative as oxygen, so it can't handle that negative charge well. So nice. And then when it's a secondary electrophile, it doesn't really worry about crowding like an SN2 because it's not having to do a cone of reactivity thing. It's hitting these hydrogens on the outside. So 6 hydrogens to run into is better than just say 2 or 3. So boom, can hit one of the 6. And that reaction works great. So tertiary electrophile. When we looked at SN2, not E2, when we looked at SN2, tertiary was too much crowding, right? But in this case for E2, it's not crowding, it's just more things to react with. It's 9 hydrogens now that it can run into. So tertiary is all good for SN2, I mean for E2. Wow, 9 hydrogens, 1 carbon away. So I can pick any of those 9. And there we got it. And this is, again, sterically hindered, strong base. Oh, and then I want you to think of an O minus like this, an oxygen with a minus charge and no resonance. Think of it as a strong base. Think of it like our classic, poster child for strong base, sodium hydroxide. So you got hydroxides O minus with no resonance. This is called an alk oxide, O minus, no resonance, strong base. There we go. SN2s for the birds. What? Just because your backside can't go backside, so the big sterically hindered backside can't get into the cone of reactivity. Like this one's too crowded to really get, and it's too strong of a base to do SN2. Okay, we'll pause there. We're gonna, next lecture, we'll talk a little more about E2. We're gonna talk about this thing called anti-periplanar transition states for E2. Then we're gonna compare everybody. We're gonna say for the next exam, for the final exam, I'm going to give you an electrophile, a nucleophile and or base, and you're going to tell me, oh, I'm going to get these possible products and I'll get mostly this, So we'll break it all down for you. And we've already started to do that. I'm hoping this will be easy for you. It should be easy for you. We've already been working on it.